Before I dive into how we find derivatives of parametric functions, just a very quick review of parametrics. Parametric functions are ones where the independent variable is not going to be x. The independent variable is actually t, which we generally say refers to time. The dependent variables, we actually have two of them. We have the y, which we're used to, but x is going to be dependent here. So x and y both depend on t. What tends to make this a bit confusing is not that x and y both depend on t, but when we graph these, they're being graphed on the xy plane. There is no t axis, so there's no obvious place to see, hey, what's my t variable equal to at any specific point? The reason that we like to do this is much like with polar functions, it's not just the final shape of the graph we care about, it's the order that the points are being graphed. So how is the shape being graphed, not just what's the final shape. So for example, I have x equals the square root of t, y equals t minus 2, and I'm saying the domain is t is between 0 and 4. I can start graphing this and say, well, if t is 0, x would be 0 and y would be negative 2. So my graph actually starts right here. If t is 1, x is 1, y would be negative 1. So I then go to that point. If t is 2, x is about 1.4, and y would be 0. If x is 3, or if t is 3, x is a square root of 3, which is about 1.75. Y would be 1. And if t is 4, x would be 2, and y would be 2. So I get what that curved piece there. What makes this really kind of nice is it's not just about what shape I get, but it also tells me, whoops, sorry about that. It also tells me the order I'm graphing in. So it's saying when the shape is drawn, it starts down here and goes this way. So it's one of the reasons you'll see parametrics get used in motion a lot. When I'm talking about finding the derivative of parametric, it's easiest to think of this as slope of the curve. To go back to my last slide here, it's because we're graphing on the xy plane. So since derivative means the slope of the curve, and I'm on the xy plane, I have to have my slope in terms of y and x, change in y over change in x. So Leibniz notation is really nice for this in that the derivative of parametric is dy dx. Note that in dy dx, there is no t in terms of telling us what it is. T will show up in this dy dx when I evaluate it, but it's not there in the notation. And this is a little tough because it feels like, okay, well, how do I find this dy dx when I have two equations, an equation for x and an equation for y? And what we do is we say, well, let's just find the derivative of both with respect to t and then divide them. So I have the derivative of y with respect to t divided by the derivative of x with respect to t. Most people choose to remember this by thinking of it as dy dt and dx dt are fractions, and that will cancel the dt, leaving us with dy over dx. It's not strictly mathematically what's happening, but it's a great way to remember it. So if I look at my example here, if I want to find dy dx, I need dy dt, and I need dx dt. So dy dt is going to be equal to 2 times cosine of t. And dx dt is going to be equal to 2t. And there is my derivative. We can simplify it a little bit by canceling the 2's, but I don't have to. But that's our derivative. If we then talk about the second derivative of parametrics, and if you have my pre-printed PowerPoint, there are some typos on there. You may want to go ahead and compare that screen here, and please make those fixes. One really, really big typo that I had to fix is right here. That should be a dx. in my PowerPoint, I know I have it as a dt. So please make sure you're fixing that. The second derivative is the derivative of dy dx, but because dy dx is written in terms of t, if I just take its derivative, what I'm actually doing is this, where I'm taking the derivative of y with respect to x with respect to t. And I don't want it to be with respect to x with respect to t. I want it to be with respect to x twice. And so after we take the derivative of dy dx, we then need to divide by dx dt again to cancel out those dt's. So in our last example, we had found dy dx is cosine of t over t. We had done that because dx dt was equal to 2t, and dy dt was equal to 2 sine t, or 2 cosine t, sorry. So if I want to find the second derivative, d squared y dx squared, I need to take the derivative with respect to t of dy dx, and I'll divide by dx dt. Now, I am fortunate in that I already know dx dt. That's 2t. Well, for dy dx, I need to take its derivative with respect to time, or with respect to t, I should say. I'm going to need quotient rule there, so I have bottom times the derivative of the top minus the top, and then derivative of the bottom is just 1, all over the bottom squared. So replacing that into my second derivative part, I'm going to have negative t sine t minus cosine t. Whoops, I'm not giving myself enough room. Negative t sine t minus cosine of t all over t squared, all divided by 2t. And that is our second derivative.